Hi everyone, I'm very happy to have Professor Stanley Chen here to join us with a great talk. And Professor Chen is now an associate professor in School of Electric and Computer Engineering in Purdue University, and he was a postdoc researcher at Harvard. And now his research covers the signal and image processing and applied statistics, and also the large-scale numerical optimization. And let's enjoy his great talk.
Thank you, Hu Ya. Thank you, Alice, other organizers, for inviting me to this conference. It's really my great pleasure to be here. When I look at UG2 challenges, I'm very, very impressed by the breadth and also the depth of this workshop that really draws a lot of people to work on the intersection of computer vision and also image processing, machine learning, everything together. What I want to talk about today is a sub-problem in computational photography / computational imaging for difficult weather conditions. And this problem is called imaging through atmospheric turbulence. And I have a subtitle for my talk, which is accelerating forward models in order to empower deep learning algorithms. So the focus of this talk will be on forward models, and I'm gonna explain what that means with the final goal of helping deep learning algorithms to do better in terms of reconstruction. To start with, I want to bring this slide to your attention that what is turbulence? Well, turbulence is really a problem about seeing things that are many, many miles away. That would be very applicable for navigation, defense, remote sensing, and other types of problems like these. The examples here should be familiar with many of you who have been capturing images that are far away. So you can see that the objects, they are jittering. You can see that the turbulence effect of the images. So in fact, this problem is not just a problem for us, computer vision scientists, it's also a very, very big problem for physics. Over the past 100 years or so, people have been developing a lot of telescopes, including very advanced adaptive optic systems in order to see through the sky. This is the CAD telescope that is installed in Hawaii. And you can see that they have two big telescopes with many, many small apertures installed together in order to see through the sky. Now, unavoidably, because you are seeing the sky, the atmospheric turbulence is going to affect your image quality. And so people develop many instrumentations to help compensate any phase distortions that are induced by the atmospheric turbulence. There's a huge collection of topics on this problem, which is the imaging through atmospheric turbulence. And the history can be traced back for more than 100 years. Now, given this breadth of topics, it is almost impossible to cover everything in a single talk. I would just want to mention that the research covers all the way from hardware to physics theory, forward model, image signal processing, and computer vision. And of course, to many people in this room, we are mostly interested about image and signal processing as well as computer vision applications. But what I want to do is to take a step backward and ask, what would be the physical forward model, which is a very important piece of information that we will need to use in order to do the image processing. So I will focus on this part for today. Now, let me explain what is forward model. The turbulent, you can imagine that it is a media. So that is the source of all the distortions. If you send an impulse, or in our case, you put a laser source, it would be a point source. You shoot through this turbulent media, and then you observe at the other end of this media. Then what will happen is that this grid of point sources is going to become something different at the receiver side. Now, if you look at this receiver side, we can see that each point in the input space is going to be mapped to something what we call the point spread function. At different locations in the input space, you have a different point spread function. The point spread functions, they are spatially varying, meaning that at different locations, you have a different point spread function. They change in shape, they change in size, they change in magnitude. This is a very, very nonlinear process. However, we can more or less say that y, which is the output, can be written as some kind of nonlinear operator h with a parameter theta applied to some kind of input x. So as long as you can write down the expression for this h theta, then we have a forward model. Now, given this forward model, we can do many things that we want. For example, we want to solve the inverse problem. Given y, if I tell you what is h theta, can you find me x? Or a more difficult problem, I tell you y, you find me the theta and x simultaneously. So this is the typical inverse problem that you want to solve in this scenario. But before we do that, we need to understand what is that h. There are 4 reasons that I want to focus exclusively on turbulence forward model rather than talking about the inverse problem. Now, the forward model has very, very important reasons to be there. The first reason is that it is really about a scientific curiosity. For many years, at least for the past a decade or so, we have been seeing a lot of work on the image processing literature that tries to approximate the turbulence using what we call the simple pixel displacement plus blur model, which is a very, very good model. Now, when you look at the this turbulence using this pixel displacement and blur model, what you would generally see is that they say that the turbulence is going to generate some kind of pixel displacement. This is what we call the tilt map or the pixel displacement map, or using our signal processing language, we call it the motion vectors. So you have a pixel in the space, you're going to move the pixel to another space. This is the first part of the distortion. And then there is a second part of the distortion, which is a blur, that you apply a blurring operator, usually a low pass operator, to the distorted image. The scientific question behind here would be, what is the pixel displacement? Yes, you say it is a pixel displacement. There are some randomness. What is the underlying power spectral density? What is that? Is it Gaussian? Is it ID? Is it correlated? Correlated in what way? What are the parameters? When you say blur, is it spatially invariant? Is it spatially varying? What is the shape? How do you parameterize it? So there are many, many deep questions. And I should also say that over the past couple of years, there are a lot of work doing GAN, generative adversarial network, that basically take a bunch of real images and then they train again and say that I can mimic the turbulence effect. This is a very, very excellent approach. It's very innovative. But I also have a challenge for this kind of approach, because when you try to simulate turbulence, do you know whether the simulated turbulence actually meet the physics law? And if I am able to synthesize the turbulence via the physical law, and I'm able to provide you faster, more accurate, and then more explainable solutions, then I think that can give us strong reasons for us to go with the physical approach than using a black box GAN approach. Another reason that I want to study the turbulence forward model is that we are mostly interested in generating data. We are mostly interested in training deep neural networks for the reconstruction tasks. However, for different simulators, the generated data will have different quality. As a result, some simulators, they are able to simulate better images, some are not. The implication to the reconstruction algorithm is that better images that adheres to the physics better, they usually give you better reconstruction results. Here is an example where we take real data, which is captured at Purdue last year, and then we apply 2 different simulators to just simulate training data. We use the same UNet architecture for the reconstruction. We don't touch the reconstruction algorithm. We use the exact same UNet architecture for reconstruction, but then we feed the network with 2 different sets of training data. One is using a very simple pale plus blur model. The other one is using our version 2 simulator. And you can see that there is a substantial difference between the quality of the images. Now, of course, this is real result, and so I don't have the ground truth to show to you, but I can confirm that there isn't any artifacts that are shown here. These are really the unwanted details generated by the wrong data. The third reason I want to study turbulence forward model is that there is also some kind of misconception in our community that all kinds of real data would be valid. In fact, there are different types of turbulent effect. You can put a camera right next to the hot air source, or you put a camera via a very, very long range turbulent effect. The images that you're going to collect will be different. For this hot air sequence, from time to time, you will be able to see a perfectly sharp image, which is called a lucky image. And this lucky image is global. The reason why this is happening is that the turbulence is so localized that you localize in time that once upon a time, you will be able to see a distortion-free frame. Now, in terms of the real long-range turbulence, you almost never get a perfect lucky frame. Or the best you can get would be some lucky pixels, and you need to fuse all these lucky pixels together. So there's a difference between the hot air and also the long range. Now, if you want to evaluate your algorithm, let's say you're trained a neural network, you say, I want to calculate its performance. Should you use the sequence or should you use that sequence? So that's a question. Now, if you want to simulate some kind of data so that you can calculate PSNRs, then you have even bigger problem. Then because a different simulator is going to give you different sets of testing samples, and then those testing samples will affect the PSNR calculations. And so having access to the correct simulator will help you do the evaluation. And finally, the reason I want to study turbulence forward model is that we all want to solve the inverse problem. And we used to see problems like these. We have the 2 norm square of the hx minus y, which is the perfect forward linear least square problem, which is also called the deconvolution problem. And then you can put your favorite prior distribution over there so you can solve this problem. In turbulence, you can, of course, replace this linear operator h by your nonlinear operator, and you can apply all the tricks that you want. However, in order to solve this problem, you need to have access to h. And you also want this h to be back propagation enabled, meaning that it has to be differentiable. And so if you look at a typical deep learning network, all these modules, they're differentiable. And so if this h is not differentiable, then you have a big trouble of plugging into a formulation like this and trying to solve the inverse problem. Okay, so these are the 4 big reasons that we want to study the turbulence forward model. And that's a very important reason that we want to focus so much on this forward model. Because if you don't understand the forward model, many of these things cannot be done. The history of imaging through turbulence is very, very long. And I cannot even include more earlier work, including Isaac Newton, Galileo Galilei's work, that they have observed these phenomena for hundreds of years ago. I will start with Andrei Kolmogorov's seminal paper, where he defined what is this atmospheric turbulence. But then I will also mention that the quote-unquote golden period happens during the 60s and in the 80s. And that is attributed to many, many great researchers in this field, including Valerian Tatarsky, David Free, Joe Goodman, and colleagues like that. They developed a range of very, very important results, helping us to understand the optics of turbulence. Nowadays, we're enjoying some books. But then when you look at the time post 2010, when deep learning algorithms are kicking in, it seems that many of these great literature hasn't been really utilized. And so I think it is very important for us to at least spend some time to understand what these wave theories are and how they can be implemented to empower deep learning algorithms. Okay, so here is a brief outline of the talk. I will talk about how does a wave propagate through the atmospheric turbulence. And then I will present two simulators that we have been building at Purdue for the past 3 years or so. I put just 1x, 20x, and 1000x right next to each topic. 1x being the speed of the simulator, and this is a relative speed. So this is the classical algorithm that simulates the turbulence. We had the version 1 simulator, which is called the collapse phase-over-aperture model, that can speed up the computation by 20 times. And then we have the newest model, which is the version 2 phase-to-space transform. We can enable the speed by 1,000 times. The work is mainly done by 2 of my students, Nick Chimit and also Julian. They are really the heroes behind this project. All right, so without further ado, let me jump right into the main topic of how does a wave propagate in vacuum, okay? All right, so this is a very simple slide that I take from Fourier optics. Suppose that you have an object plane and there is a point source. And imagine that this point source, you have a circular aperture, very small circular aperture. The wave is going to propagate from the source to the observation plane. And then this propagation equation is given by this. Now, this equation is very complicated. However, if you pay a little bit attention to this equation, inside this double integral, you have a function and then you have an exponential term. If you recognize it, this is actually the Fourier transform of whatever that you put into this parentheses. So this equation is really about the Fourier transform of this incident wave, and then you multiply with some kind of phase term, take the Fourier transform, and then some additional phase term. The z here represents the propagation distance, and then the k here is the wave number. This equation is called the Fresnel diffraction equation. It's given by Fourier optics equation 4.17. It's a very, very well-known result in the optics literature. If you send a impulse and then you have a circular aperture, what you will observe at the receiver end will be this airy disk pattern. Now, let's think about the turbulence. So the turbulence, how are you going to model that? You need to model the turbulence as a stack of many, many phase screens. Now, I need to mention that all the wave distortions, they are happening not in the amplitude space, but in the phase space. The amplitude, typically, when you're talking about long range, you do not assume any scattering effect. The amplitude, you can safely assume that they are constant. Now, what is going to change will be the phase. And so we need to model the turbulence as a stack of phase screens. These phase screens, they are drawn from the Kolmogorov power spectral densities. So if I tell you the power spectral density, then you just go through the standard process in random processes, draw this random phase screen. It's a 2D random process that you can draw from this power spectral density. So draw that. Now, how are you going to describe the propagation from the source to the observation point? You're going to take the ith layer wave equation, and then you're going to multiply with the phase distortion generated by the ith phase screen. So you multiply the wave with the phase, and then you take the Fresnel diffraction. So this FR denotes the equation in the previous slide, which is this equation. You take the Fresnel diffraction, and then you can obtain the I+1 equation. So you take a step from the source, 1 step, 2 step, with many, many steps at the end, and then you're going to see the pattern. And then the observation that you're going to see would be this distorted point spread function. So this is for one point. Now, how about that we are talking about an image? An image, you have multiple points. So for every point, you need to do this process. You need to do the Fresnel diffraction and then also the phase screen multiplication, propagate one step, propagate another step, all the way to the receiver end. Now, the correlation between this point and that point is enforced by the overlapping in the phase screen as you propagate through this media. And so the spatial correlation doesn't come from the blue. It is that as you try to calculate this Fresnel diffraction, you're cropping the phase screen at different locations. And therefore, ultimately, if the 2 points are close, the point spread functions, they will look very similar. And so how do we understand this forward model then? Well, if I give you a clean image, you send it through the turbulent media, you're going to get a distorted image. And this H theta can be represented as Fresnel, Kolmogorov, etc., for whatever number of layers that you need to assume. And don't forget that you need to repeat this process for every pixel. And so if you have a cameraman image 256 by 256, you're talking about 65,000 pixels. And you need to repeat this Fourier transform and then Kolmogorov power spectral density, and then another Fourier transform, etc., for 65,000 pixels. And this is extremely time consuming. So when we started this project in 2017, we went through a lot of textbooks and also papers. And I was telling Nick, my student, that let's just try to reproduce some of these results so that we can have a better idea of what that is. And of course, Nick was not very happy because this really is taking forever to implement this and then also to get a result. To get a result from this method, this is called the split step propagation method. We're talking about 20 to 30 seconds per frame for a very, very small frame. And so you can imagine how much time that you need to spend or to just generate one video sequence. And so we look at the problem and we spend at least 2 years just to go through all the literature to understand how we can speed up the process. And so in 2020, we published our first simulator, which is the version 1 simulator. This idea is called the collapsed phase-over-aperture idea. The idea is that when you look at the turbulent media, originally it is modeled as a stack of phase screens. What we want to do is that we want to collapse. We want to just use one overall screen to represent the entire stack of screens. Now you may wonder, how can this ever be possible, right? You have 10 screens, how can you just use one screen? Now the key enabler of this idea is that for every point on this collapsed model, if you can carefully assign the phase to every pixel in this collapsed model, you are actually able to reproduce exactly the collapsed model. Okay, so how is it possible? Let's look at this image. This image, for every pixel, you have a point spread function, and they are spatially varying. Underneath each point spread function, there is a local phase function. So there is a one-to-one correspondence between the point spread function and also the local phase. Look at this pattern. The point spread function, of course, is a square pattern, right? So you have different values. We all understand what that is. The local phase function is a function that is defined on the unit disk. And you have a unit disk because you have an aperture, a circular aperture. You need to take the Fourier transform of this local phase screen, and then you take the magnitude square. Then you will be able to get this point spread function given by this equation. So if I go to this phase screen, if I am able to tell you at every location the local phase screen, and then you can take the Fourier transform, etc., you can get back the point spread functions. Then that's it, right? So if you know the phase, you know the point spread function. If you know the point spread function, you can do the spatially varying convolution. You will get the distortion you want. So all the complication is going back to whether you are able to find the local phase at this point, and at that point, while you're adhering to the physics that we wanted from the stack of the layers of turbulence phase screens. And so in order to do that, we go all the way back to 1975, and that is a solution to this problem. The solution is called the Zernike polynomial and phase and atmospheric turbulence by Robert Noll. So what he says is that you have a local phase function given by this phi of rho. In this phi of rho, you can have a representation given by the Zernike basis and also the Zernike coefficients. So this equation should be familiar to most of us who do signal processing. It's just a linear expansion idea. So what is this Zernike basis? This is the snapshot of the Zernike basis. You have many of these orthogonal functions in the unit disk. Now, there are different representations. For example, this first two Zernike representations, they really denote what we call the tilt, or we call it the pixel displacement. If you look at this diagram here, this is y, this is x. If you take the e to the power of jx, e to the power jy, when you take the Fourier transform, that will translate to a delta function in space. So that will really give you the shift. These, they are called the blur, or the high order aberrations of the Zernike basis. So the Zernike basis, they're sort of unknown, they're deterministic, they're known to us. The main trouble is about the coefficients. If you are able to draw the appropriate Zernike coefficients, then you would get the phase. If you get a phase, you can get the points per function, and then everything is solved. So all we need to worry about is how are you going to get the Zernike coefficients so that it satisfies all the physics requirements. So we trace back to the literature, and again, Robert Noe gave us half of the answer. The Zernike coefficients, they do need to have some kind of correlation, and the correlation comes in two parts. The first part is called the intermodal correlation. The other one is called the spatial correlation. For the intermodal correlation, what it means is that you look at one pixel location, and then you look at two different Zernike polynomials. And then there should be a correlation between these two. By correlation, I mean that you take the expectation of the product of these two terms, aj and aj prime. Now this theta would denote the location. So here you have theta prime, here you have theta. So two different locations. The intermodal correlation tells you the correlation between these two Zernike coefficients at the same location. Now, if you look at the spatial correlation, this is about the same Zernike basis, but then at two different locations. And then you can calculate this correlation. If you know these two, you will be able to just draw from the Gaussian with this covariance matrix. And then you'll be able to draw the Zernike coefficients, then you form the phase, you get the PSF, problem solved. Generating the intermodal correlation is not too hard. It was given by Robert Noe's original paper. He says that this representation has the advantage that the integral, which is this, is not too long, 3 lines, appear in equation 25, can be evaluated in closed forms, the appendix, which is another 2 pages of equations. So it's not too hard. We can implement that. We can get the numerical results, and this is the correlation now. So we can do that. The spatial correlation, however, is a little bit trickier because there isn't any work that explicitly tells us how do you correlate these 2 points in the space. So we did a treasure hunt. I call it treasure hunt because when you go to the Journal of OSA, you need to read all the way back to the 60s and find the appropriate paper to find a solution. So this is a treasure hunt. So we find this treasure published in 1992 by Gary Channon. So what he says is this. If I have 2 apertures, well, of course, by that time he's studying the Keck telescope. So you have 2 apertures or multiple apertures, and you have 1 star, then I will be able to calculate correlation across these 2 apertures. So when we look at this problem, we find that, wait a minute, there is actually a symmetry between this and that. Here we are talking about 2 points in the object plane, and then we have 1 camera. In Channon's paper, what he talked about is that you have 2 cameras, but then 1 star. Okay, so there's a very beautiful symmetry here. Maybe these 2 can become equivalent. And so we did this analysis, and we proved that indeed they're equivalent. 2 points in the object plane to 1 camera, and then 2 cameras in the observation plane to 1 star. There is an exact relationship between these 2. And so once we find this relationship, then we can leverage all the results from Channon's, and then we can derive all the correlations. Now, one caveat is that Gary Channon's result is limited to the first two Zernike coefficients. He didn't talk about how are you going to generate the Zernike basis for the results to other Zernike bases. And so we did another treasure hunt. This time we go all the way back to 1995 by Takado and also Yamaguchi. So they followed up the work of Gary Channon. And so they showed the spatial correlation of Zernike phase expansion coefficients. And they showed that for all the Zernike coefficients, the equation is not too complicated. It's just 4 lines. And then you have this 3F4. This is an integral that will take you another couple of lines. It's not too hard to implement. So Nick just volunteered to do it, and he made it. It was painful, but then we got this equation, and so now we have everything ready to put together and get our first simulator. And so now, if you go to MATLAB Central, you will be able to see our version 1 simulator. It is on the public domain. You can download, you can try it. It is working. And so just to convince you that the simulator is doing what it is supposed to do, we compare to the split-step propagation, which is usually referred to as the gold standard in the wave propagation literature. So we compare to the split-step propagation, and you can see that visually they look similar. Here is the tilt map, and you can see that the tilt map makes a lot of sense. Now, when we present this results to computer vision scientists, I think many of us would be satisfied. But if we present these results to optics experts, and then of course they will require even more evidence to show that the simulator actually works. And so we did experiment. We compared with the Z-tilt and also the differential tilt. These are the two standard statistics that the optics community requires us to look at. The Z-tilt is really to look at the tilt statistics taken into the product form. So you have these two locations, you look at the tilt, and then you have an ensemble average of all these, you take expectation. Then you can track this tilt statistic, it's called the Z-tilt, and we can show that our Z-tilt matches, the simulation matches with the theoretical very well. Here is another statistics called the differential tilt. The differential tilt measures the tilt statistics using the square difference. And again, you can see that there is a pretty good match between theory and also the simulation. Another thing that the literature usually look at is whether your ensemble average of all these points by functions at the same pixel location, when you take the average together, will they give you so-called the long exposure pattern? Now, for the long exposure pattern, there is a closed form expression, and you can measure again, you can compare against the theoretical expression. So if you're doing properly, then your long exposure should match exactly with the theoretical long exposure. Same for the short exposure. So the short exposure is the points per function without the tilt. So think about the Zernike coefficients. Remove the first two Zernike coefficients, then you have this short exposure pattern. You take the average, compare with the theoretical equation. If they match, you're good. And so the simulator that we built, we do have a very, very good match with the long and short exposure patterns. That justifies that the statistical properties, they're all satisfied. Now, about the runtime, we all care about the speed. It turns out that the new simulator is about 4 seconds without GPU compared to 120 seconds without a GPU. This is about 20 to 30 times speed up. Of course, when you if you pay attention to the this result, you notice that they are using a 65 by 65 grid over a 257 by 257 image. We are using an 8 by 8 grid for a much bigger image. So you may wonder, okay, this comparison may not be fair. However, I should note that there isn't, the comparison is indeed fair, because here when they have the 65 by 65, the number of tilts that they're able to generate will be limited by the grid size. For us, the number of tilts is actually dense. So every pixel we will have a tilt map. And compared to the 65 to 65, they have a limited number of tilt. What we observe is that the tilt requires a lot more precision than the blur. The blur, you can do some kind of interpolation, but then for the tilt, you need to have a very precise information. And so this 4 second compared to the 120 second, this 20 to 30 times speed up is actually quite significant, considering that we offer a much more precise tilt map than this previous simulator. So this is the version 1 simulator. It works reasonably well, and we are very happy with the simulator. However, we very quickly run into a problem, which I'm going to explain in a second, that leads us to the second version of the simulator, which is the phase-to-space transform. It's a submitted paper, and then the code will be coming out very soon. So you may wonder, what is the problem? So after we have built our version 1 simulator, I asked Julian, another student of my lab, to just generate a data set, and so that we can try to train a deep neural network for reconstruction. And so Julian took the data, and then Julian took the simulator, tried to simulate some data, and a week later he reported it's taking forever. Forever means that everything's taking so much time. And so Nick and I was very surprised. We thought that we are already much faster, and indeed we are much faster than the split step propagation, but we are still pretty far away from being able to simulate a large data set. So we go back and look at the problem, and here are the 2 reasons why it's not working well. The first reason is that, as I mentioned, every point spread function, you have a local phase. In order to get the point spread function, you need to take this Fourier transform, magnitude squared e to the power something. You need to repeat this for every pixels in the space. That's taking forever. Another source of problem is that you have so many pixels, and then each one you have a different point spread function. And so now if you convolve this image with all these point spread functions, you have a spatially varying convolution, and that is also taking forever. And therefore, the combination of these 2 sets a very, very big bottleneck for our simulator that we need to find a way to overcome. And so as someone who did signal processing in the past, so what our idea is that we are going to look at each point spread function, and we want to express the point spread function as a set of basis functions. So you look at this point spread function here, all these you can imagine that they're Gaussian basis. Okay, so Gaussian basis, and then its derivatives and so on. So here is the point spread function. You can write it as a linear combination of all these basis functions. And these betas, they are the coefficients. So at this pixel location, you have this PSF, and therefore you have this set of beta. However, the basis functions, they are the same. Now, when you go to another pixel location, the betas will become different, but then the basis functions will remain the same. What it means is that you take this clean image, and then you just need to pre-filter the image with all these bases, pre-filter them, and then at every pixel location, just calculate all these betas. Then you'll be able to form this combination of all these edge. And also, you don't even need to calculate the edge explicitly. You can just directly get the blurred image using this combination of basis idea. Now, I should mention that this idea is not new. You can imagine this basis expansion, linear expansion. This idea has been here for a long, long, long time. These are just 2 example papers. They are talking about these ideas. However, when you have this idea in place, you can do something really, really interesting. You take this image. This is the clean image, ground truth image. You can convolve with all these bases. And then you get this blurred images by different basis functions. Then you multiply with all these betas, which are the coefficients. Once you get these coefficients, you multiply them together, you add them together, you can get this distorted image. Now, the question is, how do you get these betas? How do you get these coefficients? I can easily generate the Zernike coefficients. That's not a problem. I can generate Zernikes is not a big deal because I can go to the Kolmogorov power spectral density. I can look at the statistics. I can look at this the till correlations. I can look at spatial correlation, and I can draw these. That's not a problem, and that's available from version 1 simulator. But going from the Zernike coefficients to these basis coefficients, that's a big question mark. If I am able to overcome this block, then everything else will become easy. So that leads to our second idea, which is the phase to space transform. Apart from this spatially invariant convolution idea, the phase to space transform is our second idea that makes this entire simulator work. So what is it? Now, the input to this phase to space transform is a set of Zernike coefficients. So it is the phase representation, and I want to get the representation in the space. So I need to have a transformation from here to there. In the phase domain, the bases, they are the Zernike bases. And then in the spatial domain, the bases, they are, for example, the Gaussian bases. Of course, we have better ideas of how to generate these bases using a data-driven approach. But imagine that you have this phase representation. You have all these basis functions. You have the representation coefficients. You want to go to there. What you need is that you need to have a transform that converts these Zernike coefficients to the betas. And this is a nonlinear transform. We can do it analytically, but that will take forever because the equations are very complicated. However, in the age of deep learning, we can build actually a very shallow network. It's a 3-layer network. It's actually just fully convolutional neural network. The input dimension would be 34 because we have 34 Zernike coefficients, and then the output will be 100. This is arbitrary. We just try 100 coefficients. That seems to be enough. You're just turning this 34-dimensional vector into a 100-dimensional vector. And once you have trained this network with enough data, you can just do this on the fly. And since this network is so small, you can parallelize it, and you can repeat this calculation for every pixel using GPUs, and that can speed up the process by a lot. And not only that, because of the phase-to-space transform, you can also enable something that the version 1 simulator is not able to enable, which is the phase interpolation. In version 1 simulator, if you have 2 points in the space and you want to interpolate across the grid, okay, then you can only do the spatial correlation, spatial interpolation, which is the superposition of pixel intensities. This is actually not correct in the physics. All the waves, they are added in the phase domain. It's the phase functions that gives you this distortion. And so you need to interpolate in the phase domain. In version 1, you're not able to do it. But in version 2, since we have the phase-to-space transform, you can just interpolate everything in the phase and then apply the phase-to-space transform. You can get all the points of functions correctly. And note that if you do the interpolation in phase, you will be able to get back something called the lucky effect. In the spatial domain interpolation, you're not able to do that. We also did a lot of experiments with the color simulation that we showed that with the new simulator, you can do the color simulation pretty accurately as well. So a few slides just to convince you that the new simulator, version 2 simulator, isn't sacrificing any accuracy at all. So we look at the till statistics again, the Z till differential till, long and short exposure. Compared to our real data sets, you can see that there is a very, very good match between the physics and also the reality. We also try to compare to some kind of long, this is not long range, this is hot air sequences. So we are able to simulate these hot air sequences. Here is a snapshot of our results on GPU using the split-step gold standard method. It takes about 24 seconds per frame, and then using the version 2 simulator, we're going down to 0.026 seconds per frame. To just give you an idea, if you want to synthesize a data set that contains 1,000 video sequences, each sequence contains 100 images, this simulator will take you about a month to generate. This simulator will take you less than an hour to synthesize the same size of the data set. And then we also This experiment is an experiment by training the UNet with different simulators, and you can see that our simulator, the new simulator, is able to generate images with less artifacts. Here it will be the synthetic experiments. We're using the split standard, gold standard to generate the testing data set, and then we use a different simulator to generate the training data set. And you can see that the new simulator does offer improved PSNR values. Let me wrap up by telling you some ongoing work, and then I'll take some questions. One of the very important things that we have been looking at is this forward model, this H theta, now a differentiable model? What is the form right now? If you look at this expression, this is the version 2 simulator, you notice that all the observation pixels, they can be represented as a summation of all these individually blurred pixels. And this is pre-computed because it is spatially invariant convolution. These betas, they are the parameters that you need to estimate. And so it is now written in a linear form. That's phi m, they are the basis functions that you know, so they can be pre-computed. And if you know these betas, that will become a linear model. If you don't know the beta, you need, that will become a bilinear function, but that's also not, it's also a reasonably studied problem. Now, some of you may wonder how many betas that you need in order to encode this image. I would say that you probably need very few betas. The reason is that you can chop the image into a grid of anchor points, and you just need to evaluate at all these anchor points. Why is it possible? Because of the phase-to-space transform that you can do all these interpolations in the phase. So once you know the anchor point betas, the rest you can just interpolate. And so ultimately, the number of parameters that you need in order to solve this problem may not be that huge. Now that's my conjecture. I haven't started to look at this problem very carefully yet. We're about to do some experiments, but I have a very, very good confidence that the number of parameters may not be that big. We are also actively doing experiments. We built this Purdue heat chamber in our lab. This is a pseudo-real computational photography setup where we put 3 heat chambers. The distance from the object to the camera is about 20 meters. And then we put an LCD screen. We display point sources. So these are just dots displayed on the LCD screen. And then we see through all these heat chambers. Then we can look at the points by functions. If you turn off the heat chamber, you can get a ground truth. Turn on, you can get a turbulent distorted image. Then you can characterize a lot of these random effects. So we are building that. We are also actively going outdoor to collect data. So these are the real data that we captured last summer, and we are going to collect even more data this summer. There are also many collaborations going on between us and also the Air Force Research Lab in Ohio. So this is the Turbulence Restoration Challenge 2022 that we are planning to launch between us, University of Dayton, and also the Air Force Research Lab. So the idea of this competition is to ask participants to develop restoration algorithms using the real training samples that we provide. We ask the participants to develop the restoration algorithms, and then we are going to provide some kind of classification neural networks. There will be a suite of classification networks, and then we will ask the participants to return us the classification labels. With many consultation with the experts in the Air Force, we conclude that this set of images will probably be the most appropriate for this competition. It would be the text images because you will have some level of variety. You also have the control of the resolution. You also have the control of the size. You can do a lot more an in-depth analysis of the turbulent effect using these kind of patterns. So stay tuned. We will provide more information as the time comes. And finally, I want to do a short advertisement of a undergraduate textbook that I've been writing. It is called the Introduction to Probability for Data Science. It's a very new book. It's a brand new book on probability. It's also a free textbook. This is going to be delivered to students for free via PDF, and they can also get discounted hard copies through University of Michigan Publishing. Now you ask, why do I want to write this free textbook? I've been teaching the undergraduate probability for many years, and I can see that we do need some effort to remodel some of the textbooks. We need to connect better to with the data science and probability. We want to prioritize some key concepts. The textbooks here, they're just getting to a point that students don't want to read. Some of the concepts, they are either too vague or some of them they're just too deep. So we want to keep the rigor while we want to ensure that students can understand the idea. There's also a very good integration with the Python programming in this book. So if you're interested in this book, you can go to my website, you can find this textbook, and I will really appreciate your feedback. So finally, I want to thank all the collaborators, especially folks at the Air Force Research Lab, Dan Lamasta, Michael Rucci, and also a longtime friend, Keigo Hirokawa at U of Dayton, who provided a lot of help. And also, of course, my students, Nick, Juan, Abhiram, and Yash, they also contribute a lot to this project. I have prepared a pretty long list of references. I'm going to post a set of slides on my website so that you guys can go there and download the set of slides. These references, they are really here to help audience. If you're interested in this topic, you want to learn more about this very, very rich literature on turbulence. Here are some of the very old papers, data sets, simulators, also reconstruction algorithms, newer ones, older ones, and also our publications. And with that, I will stop, and I want to say thank you again, and I look forward to get your questions.